Yep.
Yeah, okay, so we have Liu Yang. She's graduating now under Carnegie Mellon. To tell us about testing and learning and all those.
Okay. The notion of interaction is a unifying theme of my thesis work. So in this talk, I will discuss, under the theme, we've explored new models and results for property testing and computational learning. Okay. Broadly speaking, property testing is the study of the following class of problems. Given the ability to perform queries concerning a particular object, say a function, we want to determine whether the object is supposed to have a predetermined property or actually epsilon far from having that. The task should be performed on basically by inspecting only a small portion of the entire object, possibly random selected a small portion of the entire object, and we want to allow a small probability of failure. One motivation for property testing is that it can be viewed as a pre-processing step before learning. Okay. As usual, we have this setup. We have instance of space X, which is n-dimensional real, and we have distribution d over X. The testing the function maps X to a boundary value. A property P of the Boolean function is a subset of all Boolean functions. For example, it could be linear threshold functions, abbreviated as LTF. And we measure the distance between the function f and the property P as the minimum over all functions G, satisfying the property. The probability that f and G disagree on a random point selected from the data distribution D. Okay, right, so we assume the algorithm is given a distance parameter epsilon. The algorithm should accept with at least probability 2/3 every object that has the property, and it should reject with at least 2/3 probability every object that has distance more than epsilon from any object having the property. So if there's epsilon over too far, it's a gray area, and the algorithm could behave arbitrarily. So for example, testing linearity of functions, right? The tester can get the value of function f on axis of its own choice. If f is linear, then the algorithm should accept with probably at least 2/3. But if the value of f must be modified more than epsilon fraction of the domain elements, so to become linear, then the algorithm should reject with probability at least 2/3. If f is close to linear, then the tester can accept or reject. Another example we studied in this work is union of the intervals. Suppose the target function is exactly like what I draw here. Okay, so let me ask you: is this union of at most 4 intervals? Of course, yes. Is this epsilon far from union of 3 intervals? Well, it depends on how much probability mass you need to flip to make it that way, right? Right. So a major motivation for property testing of Boolean functions is that testing can serve as a pre-processing step before learning, basically to determine whether learning with the given hypothesis class is worthwhile. So query efficient testers has been constructed for common hypothesis classes in machine learning, for instance, LTFs, Hunters, DNFs, union of intervals, decision trees. Our goal is to do testing with fewer queries than learning. Ideally, it would be really desirable to have this query complexity of testing independent of the dimensionality n and have polynomial dependence on the distance parameter epsilon. Okay. So membership query has been a type of query people use in the standard testing model. Most testing algorithms rely on the ability to query functions on arbitrary points. In other words, we basically let the algorithm to construct its own feature vectors and then ask the function value of it, right? So ask the oracle the function value of it. So there has been work for testing various family of Boolean functions over n-dimensional Boolean cube using membership query. So this table gives the results for testing these basic Boolean functions over n-dimensional Boolean cube. Interestingly, we see for all these families, the query complexity of algorithms independent of dimensionality n, whereas learning those function classes under uniform distribution has dependence on n. However, there's a problem. Okay, so the problem is, again, membership query, namely the ability of querying function on arbitrary points in the domain, is unrealistic in most machine learning applications. The reason is the constructed points to query oftentimes lie outside the support of the distribution, or they're completely rare points. So the experts usually are humans. They do not know how to classify. For instance, when learning to distinguish pictures of dogs versus picture of cats, which is kind of a toy problem in object recognition problem in computer vision, we can actually have queries such like this, right? So is this a cat or dog? More seriously, in medical diagnosis applications, when a computer generates the medical files or lab results, it will most look like the like of the consistency of the medical results or lab files of a real human being. So the physician who need to label this kind of lab results as malicious or benign, they wouldn't know how to classify it, because to conduct further medical examinations, they wouldn't actually need to see the real patients, but because no such real patient exists, so this whole process will fail. Right, those are examples indicating membership queries may be unrealistic because human cannot always make sense of artificially constructed examples, which are not typical in nature. There are various ways to resolve that problem, but there's another problem. Even if the point is actually in the support of the distribution, it's still difficult for human to answer the membership query. For example, consider the problem of classifying movie reviews as positive or negative, right? So here's a valid review of the movie. Most of us here wouldn't have any problem of classifying this movie review as negative, right? However, in a typical machine learning approach to this problem, we would represent this sentence simply as a list of words that show up in the sentence without the order. This is called the back-of-words representation. Basically, it is a Boolean vector where each word is one dimension and has the entry 1 if the word appears and 0 otherwise. So there's various reasons for doing back-of-words representation. But the point I'm trying to convey here is that the object the human expert labels typically has more structures than the internal representation of that object in the machine learning algorithm. But although the extra structure usually, if you run experiment, this extra structure usually are information theoretically redundant, because we already could construct algorithm based on the back-of-words representation with 99.999% accuracy empirically. However, this extra structure can be very important in helping the human being to provide an accurate label. Okay, so this is an important point because the membership query will construct examples in this internal back-of-words representation that looks like the words on the left, okay? And it is very difficult for us to convert that into a valid sentence, even it actually corresponds to one, right? So what we need is a type of query that directly uses these sentences, such as one on the right, that could be found in nature, for instance, on the web. So there were some efforts to remedy all these problems I just mentioned, but these attempts have their own issues. But in the end, the machine learning community chose to move on, in other words, abandon membership query. The alternative has always been around. It's called passive learning model, which does learning from random examples taken from nature. Right, although it doesn't suffer the strange example issues we just mentioned, but it has no control on which examples will be labeled, right? So it seems quite wasteful because many of these random examples will carry little non-redundant information. As a result, more recently in machine learning, there has been a revival of interactive learning in the form of active learning. The idea is that we get a pool of random unlabeled examples, okay? And then the algorithm can request the label of any example in the pool. The hope is that by carefully choosing only the informative examples, we can reduce the number of labels necessary for learning. Okay? So the active learning does not suffer the strange example issues faced by learning with membership query. In this work, we bring this well-studied model in learning to the domain of testing. Okay? In particular, we assume that in active testing, our algorithm can make a polynomial draw of unlabeled examples from the underlying distribution, and then we can make a small number of labeled queries, but only over the unlabeled examples drawn. As usually, the unlabeled examples are viewed as inexpensive, whereas these labeled queries are viewed as expensive. Formally, a tester for a property P is a randomized algorithm that must distinguish with high probability from functions in P and functions that are far from P. Okay, in the standard property testing model introduced by Rubenfeld and Sudan, a tester is allowed to query the value of functions on any input in order to make this decision. We consider instead here a model in which we add restrictions to the possible queries. Here's a definition. Right, an S-sample Q query epsilon tester for P over distribution D is a randomized algorithm A that draws as cheap samples from D, sequentially queries for the values of F and Q, supposed to be expensive queries of these samples, and then accept with probably at least 2/3 when F is in P, reject with probably at least 2/3 when the distance of F between F and P are more than epsilon. Right, so we typically think of the S unlabeled examples as being inexpensive again, and the Q queries as being expensive. So we can describe the three models we are interested in this study by the fact that the active testing model uses a poly n number of unlabeled samples. Passive testing uses as many labeled queries as number of unlabeled examples. And the membership query model basically saying, okay, the same is basically equivalent to say the number of unlabeled examples is infinite when the distribution is uniform.
What do you mean that you draw S samples from this? So it means that you have some distribution of over all samples in property T, and you drew not only one F, you take a S F.
There's a distribution D.
Yes,
Just
but
take S.
No, there is a distribution over the inputs.
Yeah, that's right.
distribution over inputs of F.
Yes.
You remember the analytic test?
Yes.
So yeah, there is this sample from this. But you want this then, but you want to compare the process to your
But what?
linearity under
But what's the difference between S and Q?
So yeah.
You draw S samples from the underlying distribution D.
You don't ask the function value. You don't ask the function value of all samples. You get many samples. You can do this. And then you ask the function value only on some of them.
So when you actually, the membership query model is equivalent to say S equals to infinite. You can, right. However, the
That is a bit confusing. I mean,
it's important to make the distinction. So membership query, it's equivalent to say you have infinite number of points that you could make, right, non-labeled sample in the pool, whereas the active or passive tester, right, the active tester say you can only draw a poly-n number of samples from this distribution, rather than you could query arbitrary points in this domain. Right, so the question in this setting is that so whether for a given concept space, the number of labels needed for testing is smaller than the number of labels required for learning. So for example, later on, I will show you that active testing union D intervals can be done with order 1 label requests, whereas it's known to require omega square root D samples for passive testing by a Birthday paradox, and it requires omega D for learning. So I will show a number of properties important for learning can be tested with substantially fewer queries on our testing active testing model than that is needed for learning or passive testing. So I summarize these results in this table for union of D intervals, the first row. Active testing uses number of queries independent of D. This is cool because learning requires number of samples linear in D, because the basic dimension is 2D for union of D intervals. And the passive testing will require square root D. For testing linear separators on the third row in n-dimensional real, we show that both active and passive testing can be done with order square root n queries, which is substantially less than the omega D needed for learning. That is a long-established lower bound for learning, omega n, right? N is the dimensionality. Also, we get a new upper bound for the passive model, for the passive testing model. It seems like, if you look at this table, it seems like the active testing query complexity have a rich structure. It spreads from the left of the query complexity spectrum, which is a member query, to the right of the spectrum, which is a passive-like. And the dictator lower bound actually is a very general lower bound. It says like even like a simple function class as dictator require at least log n queries in active and passive models. So let's look at testing union of the intervals. The VC dimension of union of the intervals is 2D. So learning the union of the intervals requires at least omega D queries, right? By contrast, active testing union of D intervals can be done with number of label requests independent of D for any distribution. So to keep things simple for now, I suppose we're having what we have is uniform distribution. The proof of the theorem relies on a new noise sensitivity characterization of the class of union of D intervals. We define noise sensitivity as the noise sensitivity, the local delta noise sensitivity of function f. Right. So the noise at point x is the probability that fx disagree with fy, while y is randomly drawn from the delta neighborhood of x. And the noise sensitivity of function f globally is simply average over all these noise sensitivity delta given x over the random draw of x along the, according to the distribution. Right. A simple.
This is a continuous domain, so how do you define the noise in this case? Usually, I mean, the usual definition of noise sensitivity is, let's say, for Boolean function, then
right.
What do you do?
The usual definition is they draw a random pair of x, y. They pick the pair of x, y together. Here, different. What is different here? You pick. Yes. That's on the line, real 0 to 1. That's right. So you use a random sample on the uniformly. This is supposed uniform distribution on the real line between 0 and 1.
Yeah, but how does the y? How is y? What does y near delta x mean? That y is just within distance
of delta of x. Yep. Okay. So a simple argument allows to have this proposition that unions of D intervals have relatively low noise sensitivity. The converse is approximately true, although it's harder to prove. For delta small enough, okay, every function have noise sensitivity not much larger than D times delta is close to being a union of D intervals. the idea is the idea is basically if noise sensitivity is small, then not much probability mass needs to be flipped to get down to union of the intervals. Okay, first, the easy half of the proof is this lemma, which states that union of the intervals have low noise sensitivity. The proof just requires a little bit of calculus. We see because the union of the intervals has 2D boundaries, right? And the probability a random point x lands within distance delta of one of these is at most 2D times delta, right? So if we draw a random x and y subject to x and y being within distance delta of the boundary, as x being within distance delta of the boundary and y being within distance delta of x, then the probability that x and y land on the opposite side of some boundary is at most 1/4. Right? So multiplying all these together, we get a bound on the probability that x and y lands on opposite side of some boundary, and that given that they're within distance delta of each other.
Can you explain why the 1/4?
Oh, that is coming from the integration.
So x is just some point within distance delta.
Right.
But no matter what x is, like a random y in that.
So-
About, like, what are the cases where like x is like right on the boundary, and right just to the right of the boundary, then wouldn't y be on the same side of the boundary half the time, and on the opposite side half the time?
So we're interested in when x, y, you pick a boundary, and we're interested in the case where x, y is on the opposite side of that boundary. And to do that, to narrow down to 1/4, you're right, it requires some integration to calculate that quantity.
Trying to eyeball the case where, like, we have like a long interval and x is right on the end of the interval. Wouldn't y cross the boundary basically half the time?
Yeah, but the definition is on a level, it's on a level.
This is right. But it says the probability that y crosses the boundary given that x is the distance. I'm thinking about the condition on particular x.
So it's not a condition.
It's not.
The noise sensitivity, you average over a pair of closed points.
Just for an average x.
Okay.
Right. The main part of the proof is this lemma, which is harder to show, which says that if delta is small enough, then any function far away, far from every union of the intervals will have noise sensitivity noticeably larger than d times delta. The idea of the proof is based on the principle of self-correction, showing the contrapositive. If we start from any function f with small noise sensitivity, as the one I draw here, we first smooth it by taking the expected value conditioned on a small neighborhood around each point, and then we threshold that smoothed function. We call it, for instance, g, to get a Boolean function f prime. Okay. So because f has low noise sensitivity, we know that this function f prime isn't too far from the original function f. But again, because of low noise sensitivity, we also know f prime is a union of the most d times 1 plus epsilon over 2 intervals. And the way we show this implies within epsilon of some union of the intervals. So functions with low noise sensitivity are close to union of the intervals, or conversely, functions far from union of the intervals all have high noise sensitivity. So putting this all together, we get this tester. We fix the small delta, and we estimate the noise sensitivity, except if and only if the estimated noise sensitivity is the most d times delta times 1 plus epsilon over 8. And this quantity, this tester is correct by the two lemmas I just showed you and the standard turn-off bound argument. So I want to point out intuitively why the noise sensitivity only work. This strategy, right? This local notion of noise sensitivity, this kind of strategy, they only work for active model, right? So passive cannot do this because in general it needs a lot of, say, omega square root d examples by birthday paradox before a pair of two examples getting very close to each other, right? So in passive model, all those are expensive labeled examples. Right, so, but however, in active, those are unlabeled examples. So we basically go through these inexpensive unlabeled examples until we get two examples really close to each other. And then we just query the labels of these two particular examples.
This would not be a problem if you were just allowed to pick those points as well. So there's something artificially restricting yourself to,
Right.
to just
Right.
getting
That's
something
right.
from the distribution. And for example, in testing bipartiteness or something like this, you draw a set of vertices and you query all edges inside them.
That's
Obviously,
correct.
these edges
That's
are
right.
overlapping,
So that's a more powerful kind of model than
Yeah.
the one we're studying, right?
What? Real life.
Yeah, of course. Yeah. It's just it seems like
Not artificial.
you are no, it's not. I think it's artificial. It's just we have standard testing. What things we call normal passive testing, in which you get correlation. It's indirect because when you sample vertices of a graph and then you look at the values of all pairs of edges, it's correlated. Even though it looks like you pick random thing, it's not what you query. So I mean, I think the passive learning model, passive testing is not like it's not just like getting random examples and doing something. That's all I'm saying.
So if it's not a uniform distribution, so far I just showed you how to do testing for union of the intervals under uniform distribution. But what if it's not a uniform distribution? There is a standard trick where we can just take a few unlabeled examples at random, and then that will gives us enough information about the underlying distribution, and then we can just stretch and squash the axis to make the distribution near uniform, and then we just run the same algorithm.
What do you mean by stretching the...
So there is a standard trick in statistics which you can map arbitrary distributions. The CDF is corresponding to a uniform distribution, right? So another interesting class of functions are the linear threshold functions. Okay.
Just to make sure I understand, go by one time.
Don't hurry. We have lots of questions.
So, well, the point is that after about square root the unlabeled samples, you will have enough samples that are pairs of samples that are close enough, and then you can do the algorithm.
You need at least that much to get.
Okay, but
Okay, another interesting class of functions that we study is linear thresholded functions, or called LTF. In fact, this is probably the most commonly used function classes in machine learning. An LTF is specified by taking the sign of the dot product between the argument, which is an n-dimensional real vector, and an n-dimensional weight vector. Our results for LTFs are stated here. Even in the passive testing model, we find that square root n samples are sufficient. Okay? This is better than the omega n samples required for learning LTFs. Right. We also have a lower bounds on the number of samples required for testing LTFs. In the passive model, we have a matching lower bound of square root n, whereas in the active testing model, the lower bound is n to the 1/3. It would be really nice if we could close this gap. Okay. So I will start by sketching the idea behind the upper bound. There is a recent work by Mantulov, O'Donnell, Rubenfeld, and Servadio. They show that all we need in order to test LTFs is to estimate this expectation of fx times fy times the dot product between fx and y up to some constant precision. The motivation is somewhat similar to the noise sensitivity idea I just described before for testing union of the intervals. LTFs have a very nice relation between the angles of the 2 points and the probability that their labels are different.
don't they need to choose x and y such that
So it's not just, also there's labels. So the angle, yes, one thing, and if the angle is small, somehow they right, the labels supposed to be more likely to agree with each other. Right, it's homogeneous LTFs. Gaussian distribution. In fact, it should work for product distribution with bounded variance. So LTFs have, this nice relation. Again, it's between the angles between 2 points and the probability their labels actually are different. So any significant deviation from this property would be reflected from, in this particular expectation, fx times fy times the dot product between x and y. So one naive way to estimate this quantity would be, okay, I will just take some number of random pairs, and then we calculate the empirical average of the quantity in the expectation here, right? So the problem with this naive approach is that by the central limit theorem, we expect most pairs, these x and y's, to have a dot product roughly square root n, so that the variance of the terms in the average is so large that we would need order n such pairs to make the average to be within a given constant distance from the expected value. So this wouldn't work because we're trying to find a sublinear testing procedure, right? A more subtle approach is to take order square root n random pairs, and then we're just calculating empirical average of quantity over all order n pairs. And then we can apply the concentration result for the U statistics for pair points so basically from the work of Arkhorns, and to show that this actually achieves the desired precision. I should note here there's a few more complications that need to be worked out. But you can see that in the paper, but this is the basic idea. Okay. There's conditions under which the Arkhorns concentration for the pairwise U statistic to hold. So far we only have pairwise U statistics result. We don't have like triple or like high rank. There's conditions in particular because it's a Boolean function. So the magnitude, So the condition for which the U statistics result applies is that the quantity you're trying to estimate should have magnitude at least bounded, right? So in this case, through Fourier transformation, we could see actually the magnitude of the quantity which has estimate is bounded because via the Fourier transformation.
So can you state even roughly this result? If we sample, some number.
It basically says right. Okay, to get the desired accuracy, the estimate of the desired accuracy, instead of using linear order n pairs, you actually only need square root n pairs, and then you construct the n pairs from the square root n samples. So you basically sample square root n points, and then you construct pairs out of these square root n points, and the U statistics results basically tells you that even you only sample square root n points, you can still get as tight concentration as the linear size sample.
Is there any similar, in experience, it sounds very similar to the graph test using linearity testing, like very Samsonov-Litsky, they instead of picking any pairs x, y, and testing f of x, f of y, and f of x plus y, they just pick an OK point, square root n point.
Exactly.
All the pairs for
Exactly, yeah.
Yeah, so it's similar, but the proof has any relation?
But this is the proof. The proof is not that hard. In fact, you just took the Matulev's result, which worked for membership queries, and make it just change the sampling strategy. You're right. It's actually not hard. Okay, so far we have discussed the upper bounds for specific function classes, and we're now ready to formulate our notion of general dimension. Right? In learning, we have VC dimension. Ideally, we would like to construct a general notion of testing dimension that could cover all testing problems, that will be perfect. So it's based on defining a testing gain, right? And show that the min-max value can be categorized in a very natural way. So again, this definition, this notion of testing dimension, bring out a very nice connection between VC dimension in learning versus testing dimension for property testing. Specifically, we develop a general notion of testing dimension of a given property P with respect to a given distribution. So it's a distribution-specific, property-specific definition of testing dimension. It's different because VC dimension, VC dimension is a uniform convergence result. It works for all functions, right? So, however, yes, this is free node. However, this one is specific to the class, and but to make your notion, your dimension work for all distribution, for all functions, you can imagine that's really it's a larger quantity, right? So, right. And we show that these dimensions characterize up to constant factor the intrinsic number of queries you would need for testing the given property class with respect to given distribution. In fact, all our lower bounds in this paper are proved via this testing dimension. So the actual sequence of the event in testing problem is that we pick an algorithm, and then we imagine there's the adversary pick a target function. Okay, and then the data is drawn at random. However, for the purpose of analyzing the optimal probability of making a mistake, we can switch the order of events. In other words, the classical min-max theorems tells us that the optimal, which is mean over algorithm, worst case over the target function probability of a mistake, is equal to the Bayes risk, which is the minimum over algorithm, under the worst case prior. Okay, so we've denoted here the capital pi 0, the set of distributions over property P, the set of distributions over property class P, and the capital pi epsilon is a set of distributions over functions epsilon far from property class P. Right, so in our case, because the algorithm never make mistakes when f is neither in P nor epsilon far from P, so we can assume that the worst case prior is a mixture of a distribution pi from P and a distribution pi pri from functions epsilon far from P, right? So we fix pi 0, which is picked by the adversary. For a set S of unlabeled examples, we let pi S and pi pri S denote the induced distribution over labels of those examples. Okay, then we let ds pi pri denote the total variation distance between these two induced distributions. This is interesting for us because for fixed sample S, supposing the algorithm gets all the labels of those examples in the sample S, the Bayes risk is the most 1 minus ds pi pri. So now it all narrowed down, pinned down to this particular quantity, ds pi pri. To calculate the sample complexity of passive testing, so we merely need to let the adversary pick pi pri and ask whether there is a reasonable probability over the draw of S. The Bayes risk is small. Okay. So if so, there is a sufficient. This basically tells us that is a sufficiently large sample size. Otherwise, it's not large enough. So we let D passive here denote the largest Q for which the probability the Bayes risk is small is not quite large enough. So with a little additional reasoning to make this a matching or definition of testing, we have this theorem that sample complexity of passive testing is theta D passive, right? That was for passive testing dimensions. The definition for active testing dimension is a bit involved. I won't go through the detail here. Exactly. Exactly.
Coin toss, so bias point to this bias,
Right.
so that bias.
Right. So, but all you need to know about this definition of active testing dimension is that the error star quantity here is simply the biggest risk for the active testing problem when the unlabeled data set is U and the target is sampled from pi, which is probably 1/2, and the pi pri from which probably probability 1/2. So clearly the testing problem is harder when there is a low probability of getting a data set for which the biggest risk is small, and easier when the opposite is true. And indeed, we have this theorem which states that the active testing dimension tightly characterizes the query complexity of active testing.
What is S in this definition? I mean, when you define active testing, there were two parameters. S, which was the number of queries you don't, you generally sample from the distribution, and then Q was a subset, which
Exactly.
from them to get the function value. So where is S in this definition?
Okay, so yes, we're using a different set of definition. So let me tell you, there's two complications for active testing than the passive one. One is now you're allowed Boolean number of valuable examples, and you only want Q.
So S is Boolean.
Yeah. So and another complication is you got to adaptively choosing your samples based on previous queries.
So what's the essential difference in this definition from the previous one?
We're using decision tree representation in the sense that so now you can have some kind of query tree, right? So you pick these. So you're essentially picking a path, right? You make queries, and then the adaptive in the next query would be depending on the answer of the previous. But in fact, there's even more involved a notion called coarse testing dimension, which is instead of picking adaptive, we pick it like this path all at once. Right? So combinatorially, that's.
So that would be like oblivious.
Yes.
But anyway, the definition with the tree is just, that's more or less the definition of active testing. You're allowed to query adaptively.
Exactly.
Some few of the queries. So that you just plug it in, plug this decision tree definition into the same, and you just
Right.
maximize over all distributions
Right.
that take either a property function.
Right. So again, instead of biggest risk, we have the error star quantity for the decision tree based on Q samples. The difference from just a fairly pick 1/2 from pi by pi on this U sample.
Theorem, I mean, so it looks like almost the definition of active testing. This theorem requires it's direct from the definition, or it has subtleties.
If you look at this basically for this active testing dimension, what's on the right 1/4 is the same with the passive. That's right. It's constant. However, there's one intermediate step, which is a coarse testing dimension, which the quantity on the right is like 1 to the 1 over n to the c. C is a constant, so it's a polynomial. Because we want to relax by the combinatorial argument, you would have the quantity on the right would dependent on dimensionality n. Okay, so let's see some examples, like how would we prove lower bound through this testing dimension. For example, the first example is for dictator functions, and we can show that active testing dictator-shaped functions over uniform distribution requires log n queries by we're showing a lower bound through the testing dimension. Here's specifically how. We pick pi to be uniform over dictator functions and pi pri to be uniform over all Boolean functions. Okay, so you can see the paper for the proof, but the idea, if you think about it, you can see why the induced distribution over labels should be similar for those two distributions when the sample size isn't too large. So when the sample size isn't too large, the induced distribution of the S samples look very much same. And this trend actually continue up to order log n points. For instance, so why? Because any single point has 1/2 probability of being positive or negative, right, under the uniform distribution. The law of large numbers implies 2 uniform random points in high dimension have about half of the entries the same, and the other half different, right? So a random dictator function have about half probability of labeling them same versus different, which is the same as a random function. Again, this trend will continue up to order log n points. We also show lower bounds on the query complexity testing LTFs via the testing dimension. So in this case, we set pi to be distribution over LTFs obtained by choosing W, the width vector, from the standard normal in n-dimension space, in n-dimensional space, and that outputs fx, which is equal to the sign of dot product between W and x. We set pi pri to be uniform distribution over all functions. Okay, the major step of this lower bound for the lower bound of D passive basically bounds the total variation distance between the distribution x times W divided by square root n and the standard multivariate normal distribution in Q dimensions. Okay, to lower bound D active, we follow a similar strategy to the dictator lower bound, but we rely on a stronger concentration result on this spectrum of random matrices. To do that, you need to write down the covariance matrix of these. Right. So to show the total variance distance between the two quantities I care about here, right. So it's because it's n-dimensional, right? You would not only have the diagonal entries. You would for the diagonal entries is not a problem. The off diagonal entries are the problem, and they concentrate as n grows.
This happens also in the passive. I mean, what you're saying is, you have what should become distinct is the fact that this is a tree that is looking only at some of the samples. I'm not seeing some.
Then for the lower bound, right? So essentially, you don't need the trait argument. All you need is to show that the statistical total variation distance between these two distributions compared actually converges to 0 as n grows, and then that way you show a lower bound. But the complication for LTFs is that, again, you have the off diagonal entries of the covariance matrix. You have to argue that converge as n grows.
So we are talking about the covariance matrix of the samples that you are previous.
Exactly, Q samples. Right. Okay, so there's a lot of interesting problems in the active testing model. One question is what the query complexity is for active testing of LTFs, and we show the lower bound for passive. Right, there's a matching lower bound for passive testing LTFs. However, there's a gap. For active testing LTFs, we got lower bound n to the 1/3, and it is at most n to the 1/2. So it will be nice to close this gap. Another interesting problem is that how things change if we have the stronger requirement of tolerant testing, which basically tolerant testing requires to accept even if the target is just within distance epsilon over 2 far of the function class P, of the property class P, and reject if it is epsilon far from P. So for instance, is the query complexity of tolerant testing union of most D intervals is still constant?
Tolerant testing is done like parameter estimation.
Exactly. So of course, another open problem would be nice to construct a query efficient tester for LTFs under general distributions. Okay, so in the remaining time, I will sketch some results from a new model we study for PAC-learning, the class of DNF formulas. Efficiently learning DNF is the classical problem. It is one of the problems originally posed by Valiant in his 1984 paper. So a DNF formula is OR of n's of literals. There being a target function over n variables, some poly number of terms. Any Boolean function can be represented by a sufficiently large DNF. Right? Also, DNF formulas are very natural form of representation of knowledge. So, and it is easily understood by human beings. So the problem PAC-learning DNF appears to be very hard. The best known algorithm in the standard model is exponential over arbitrary distribution, and even under uniform distribution, say you can get into the log n algorithm, but it's not. But there's no known polynomial algorithm for learning DNF even on a uniform distribution. So we think of instances that have n Boolean variables. There will be some underlying distribution over them. There is an unknown target function, which is a truly Boolean function, and we'll be thinking of this as a DNF formula, and the goal, of course, is to achieve low error rate. Okay?
This is agnostic learning?
Not realizable.
Oh, so you assume the function f is DNF.
Yes.
Oh, okay.
So in our new models, we are going to look at these two kind of queries. Okay? One type of query is called Boolean query model. Given two positive examples, the oracle says yes. The oracle says yes if, in other words, the similarity function k xy equals to 1. If there exists some term in common, they both satisfy, and no if they don't. So we also have the numerical queries, which have even more information, right? The similarity function kxy equals to a number of terms x and y share in common. So let me skip these motivating examples of credit card fraud detection. Let me just emphasize on the model. In particular, we're going to model this by imagining we have an oracle that given two positive examples can output yes or no. Do they satisfy some term in common, or how many terms in common they satisfy? The question is, can we actually learn DNF formulas or their natural subclasses efficiently using this kind of extra power? So clearly, this is new. This is extra information, and as a warm-up, in fact, it is immediate to see how you would use this extra information if you had a disjoint DNF. If the target is disjoint DNF. Say again?
Disjoint DNF means the terms are disjoint.
That means for any example, it satisfies only one term and no other term. Okay, right? So that way we can partition the positive examples according to which term they satisfy. Then once we're done with this partitioning for each term, it is the conjunction learning problem, which is learn the conjunction and by intersecting all these positive examples and take the OR of the results for that. So for the case of disjoint DNF, it's really easy. So the first kind of interesting results we can get is to extend this to a natural notion of weakly disjoint DNF. Remember, DNF is disjoint if for every term, all examples satisfying that term is guaranteed to satisfy no other terms in the formula. Let us say a DNF is weakly disjoint if for each term at least a 1 over poly n fraction of the example satisfying it satisfy no other terms. So for every term, at least some non-negligible fraction of the examples satisfying it and do not satisfy any other terms. Okay, so how we're going to do the learning? Let us call those examples for any given term that satisfying it and no others distinguishing examples. And we do not, of course, know which ones they are, right? So we basically take poly n 1 over epsilon log 1 over delta samples. Among the positive examples, we can query for each pair, do they satisfy some term in common, and then we create a graph where they basically we put an edge in between a pair of positive points if indeed they satisfy some term in common. And then we can do the following for each positive example, we look at all its neighbors in the graph. Okay, so we look at those ones that they share something in common, and then we construct the minimum conjunction that is consistent with that example and all its neighbors. Okay, and then so far we have not used negative examples yet, so we discard any of these conjunctions that make mistakes on any negative examples. Of course, we're going to discard those conjunctions that some other conjunction subsumes it, right? And then we just union all this together and form a DNF as the output hypothesis. Okay, you might think it is easy to learn general DNF formula in this new model. However, the next result, this result is the hardest result. It basically says that learning DNF from random data for any for arbitrary distributions with Boolean pairwise queries is as hard as learning DNF from arbitrary distribution without these Boolean pairwise queries. Okay, and we know that the learning DNF from random data in general appears to be hard, right? So we're going to do a reduction from the problem of group learning DNF in the standard model to the learning in this new model. What is group learning? So different from PAC-learning, group learning is a problem where rather than being given one example at a time, we're actually at each round, we're given a group of poly-n examples, and they either all come from an underlying distribution D+, like positive distribution, or they all come from D-. So the task is to tell which case it is, right? And it's long established that group learn equals to weak learn equals to strong learn. So all we need to do here is we're going to connect group learn to learning in our models. So how are we going to do this? Okay, so imagine in the standard case, you're given a collection of m examples. That's what I show here. They're all positive or negative. Right, and how we're going to convert this to a problem in our model. Basically, we construct replications of examples and create a new DNF formula, which always says yes. Okay, and then you could, with probabilistic argument, you could show that with high probability, an algorithm learned from the new DNFs from Boolean pairwise queries would also group learn the original examples without those queries. And right. In fact, this applies also for approximate numerical queries. Basically means it's a multiplicative factor tau away from the exact answer of numerical queries. And it's exactly the same proof, except you make a little bit larger m, right? So that it concentrates on the expected answer. So this basically shows that approximation queries for worst case distribution does not help. Okay, however, we get some positive results for learning general DNF formula. The first one is if we're given exact numerical queries under uniform distribution, we can actually learn poly-n term DNF. So how are we going to do this? Here's the idea. We're given the positive example. Suppose that we're now collecting a bunch of new positive examples, and for each one, we ask how many terms in common it shares with the original, that first positive examples. And let's call this positive example landmark example. Okay, landmark example. So how many terms in common it shares with that one? You can give the original formula, then you have the subset of terms satisfied by this particular landmark, and you have the sum, not the or, you have the sum of those, right? So the landmark DNF, importantly, the landmark DNF is a monotone. It is unique DNF in the sense that no literals show up both positively or negatively in the formula, but it's also because you could actually see which way it is. So it's in fact a monotone. And then now we consider this learning problem given the landmark, given the collection of positive examples we know. For each one, we're told how many terms in common. We can try to learn the sum of monotone terms for each landmark. right? And then, in fact, the claim is that the problem of learning the sum of monotone terms can be solved efficiently. So the final algorithm will find a landmark positive points and do a bunch of queries. Right, the answer will be viewed as a sum of monotone terms, and learn that with the algorithm I'm about to describe to you. How would you efficiently learn sum of monotone terms? And then take another landmark and do the same. Took another landmark, so on and so forth, and eventually you OR all these results together, combine them, and get a single Boolean function that defined as at the bottom. Okay. So let's look at how we're going to solve the problem learning sum of monotone terms using a Fourier technique. Okay. One interesting property is that a subset, if a subset of the set of set S, so given a set S of variables, so if a subset of the set S, maybe the sign is changing, but the magnitude of Fourier coefficient of this subset can only get larger. Right? Because now you have more terms, and this subset is possibly containing. So that means there's a natural way to find these important sets, because if the set is important, the subset only gets larger in magnitude. So that means you can start with a small subset and then grow them, right? So this allows a greedy procedure that you can prove that it works without much difficulty. And this is one instance of how exactly this greedy procedure works. Start with x1 and try each one and check whether is the magnitude of Fourier coefficient of the S is still more than epsilon over 16 times t. Okay, so here's the algorithm. Formally, you start with singletons, and then simultaneously you do the inclusion check in the greedy way, and eventually it outputs a bunch of conjunctions, and you union them together. There's a stopping criterion guarantee. Okay, so we also have many other possible results for natural subclasses of DNF using this kind of extra power. They're shown in this table. So I do not have time to go through all these details. Open problems. So we know we can learn arbitrary DNF using numerical queries, exact numerical queries, under uniform distribution. So assuming DNF learning is hard, we cannot learn arbitrary DNF with Boolean pairwise queries under general distribution. But what about the other squares? In other words, can we learn arbitrary DNF on a uniform distribution using Boolean queries? Or can we learn arbitrary DNF under general distribution using numerical queries? We know that you cannot do it with Boolean pairwise queries, and you cannot do that with approximate numerical queries. So you will have to do it with exact numerical queries. It would be really nice to know the answers to these questions. All right, thanks.